Good afternoon. I hope everyone watching this presentation is well and staying safe during the menace this COVID-19 is continuing to create. It is ironic we as a society were making strides into enjoying the applications of virtual reality, but now COVID-19 has forced us to witness the reality of the virtual world. Thanks to the technology and fast adaptation of technology, that despite meeting virtually, we can still share and discuss good real science. Today, I'm going to talk about a new extensible set of molecular substructures for interpretable QSARs and read-across applications. I want to thank the session chairs and the organizing committee of this conference for giving me this opportunity. Though I'm the one who'll be presenting, there are several who contributed to this work. I'm speaking on behalf of my colleagues from Siom, Ruchir, and Alex, and our collaborators Nicole, Scott, and Alex Barrick from NIEHS. We will talk of interpretable models, why do we need them, and what are their characteristics, and then we will build a case for use of molecular substructures as descriptors and introduce our newly compiled chemistry-aware, chemically viable set of substructures called Saagar. And lastly, we will test Saagar in terms of active enrichment and in building QSAR models and compare them with other fingerprints and other descriptors. Why develop interpretable QSAR models? Well, have a look at this model for prediction of log P. Just see the structure descriptors that have been employed in this 15-parameter model. Molecular surface, validity of molecule, calculated dipole moment, absolute atomic charges, square root of sum of squared charges. Though the relationship seems statistically significant, but what good is this relationship in understanding what drives log P or in making decisions about designing compounds with desired log P? Such models, built with complex and abstract structure descriptors, kind of tend to bring notoriety of black boxes to QSAR models and thus lack regulatory acceptance because they are hard to understand and hard to apply. Well then, which models qualify to be interpretable? An interpretable model can point to a toxicologist, a substructure potentially rendering a molecule toxic or non-toxic. An interpretable model can indicate to a pharmacologist the structural moiety required for certain pharmacological action. It may help a biochemist generate hypotheses for a possible mode of action, or even it can guide a chemist in designing better compounds by combining substructures. What is common in interpretable models is use of substructures as descriptors. Substructures are interpretable by design because chemists and biochemists and toxicologists can relate to functional groups, molecular substructures, and motifs in terms of their possible modes of action or reaction. Therefore, models developed with them can provide chemistry-backed reasoning and thus gain wider acceptance. Substructures, in fact, have been used in cheminformatics for long, generally encoded as structural keys or fingerprints of different bit lengths or generated through automatic fragmentation and atom tracking. Rather than using any of these approaches, we decided to compile a parsimonious but extensible set of chemistry-aware and chemically viable functional groups and moieties. We call it Saagar. Saagar is systematically gathered by studying and reviewing available open source literature that highlights relationships between substructural moieties and a variety of physico-chemical, ADME, and toxicological properties. The Saagar set encodes and enumerates salient molecular features like hierarchical macrostructural classes, whether a compound is inorganic, aliphatic, acyclic, alicyclic. After all, a compound which has, let's say, 6 carbon atoms, it's a normal hexane. Its chemistry is very different from cyclohexane, and its chemistry is very different from benzene, even though they all have same number of carbon atoms, but the bonding is different, the arrangement is different. Saagar also encodes elemental makeup, ring size, ring substituents, and their positions, separation of certain heteroatoms to account for key interactions akin to 2D pharmacophores, if you will, typical scaffolds for endogenous biomolecules like amino acids and lipids, they are also encoded in Saagar collection, and some scaffolds present in common medicinal and industrial chemicals, they have also been encoded in Saagar. The current version of Saagar has 834 features coded as daylight smart strings, and we have seen that this set provides sufficient coverage of chemicals in drug bank, Campbell, and TOX21 benchmark sets. So now you know what Sagar feature set is and how it was compiled. The natural question is, how good is this newly compiled set? We designed two experiments to answer that question. Experiment number one was how effective Saagar features can be for read-across applications, and we wanted to answer that question by comparing their active extraction efficiency with other fingerprints. And the second experiment was how good an interpretable QSAR models Saagar features will yield. And to answer that question, we wanted to compare the performance of QSAR models developed with Saagar features and developed with other descriptors. For measuring and comparing active extraction efficiency, we selected three standard benchmark sets. The first one is the maximum unbiased validation set, which has over 93,000 chemicals tested in 17 different screens with very low fraction of actives, only between 0.15 to 0.2%. The second benchmark set is the unbiased ligand set. It has 42,000 chemicals tested in 20 different GPCR screens, but it has little more fraction of actives changing between 2.5 to 3%. The third benchmark set is TOX21 set, which has 41 different screens, and there are about 7,000 chemicals in this. Here, the number of actives varies from 0.15 to almost 13%. While the MUV and the ULS sets, they are constructed to have very few active chemicals by design, intermixed with numerous decoy compounds that match molecular size and overall physico-chemical properties. The TOX21 set is more practical one, consisting of industrial and pharmaceutical chemicals. After selecting three benchmark sets covering some 140,000 compounds and 78 screens, we selected four commonly used fingerprints for comparison with Saagar, and they are extended connectivity fingerprint of radius 4, MDL's max keys, PubChem fingerprints, ToxPrint fingerprints to compare with Saagar having 834 features. We computed active extraction efficiency in terms of enrichment fold for each fingerprint by leave-one-out similarity calculations for every active compound in each of the 78 screens. The enrichment fold was computed at four false discovery rates of 1%, 2%, 5%, and 10%. Each fingerprint was then ranked between 1 and 5 based on its enrichment. Rank 1 was given to the fingerprint giving lowest enrichment and 5 to the fingerprint giving the highest enrichment. The average rank of each fingerprint at each false discovery rate thus calculated is shown in this table here. You can see that at all false discovery rates, Saagar gets better rank except at 1% false discovery rate when compared with ECFP4. So in 39 of the 40 comparisons, Saagar returns better enrichment. Even at 1% also, discovery rate of Saagar and ECFP4, they get the same value of 3.5. And as we will see later, Saagar extracts analogs with higher chemistry similarity and is more interpretable when we talk of the QSAR models. And you will see that the performance is even better for Saagar in the TOX21 sets, which covers 41 different screens. Here you can see that Saagar is much better as compared to ECFP4, MAX, and PubChem, as well as ToxPrint at all false discovery rates. In the 5 fingerprints compared, Saagar has the highest extraction efficiency. And now let's look at the quality of the extracted analogs, because that's very important in selecting surrogates for read-across applications. Here is an example. We selected chrycine as an active query from the TOX21 hydrocarbon receptor set. Using all 5 fingerprints, we computed similarity of chrycine with the remaining compounds in the aromatic hydrocarbon receptor set. What is shown here is 5 structures such that each one is in the top 2 closest compounds by 1 or more fingerprints. Similarity to the closest compound is shown in blue in this table, and similarity to the next closest compound is shown in red here. In order to pick the chemistry similar surrogate, we have to look at the extent of similarity, differentiation between structures at given similarity, scaffold similarity in terms of number of rings, number of substituents, their positions, etc. If you look at max fingerprints, they give very high similarity with compounds A, B, C, D, and even with compound E, which does not have the right number of fused rings and has an added substituent, max gives very high similarity. And so is the case with PubChem. What that means is that PubChem and max fingerprints, they lack features to resolve between number and arrangement of fused rings. If you look at ToxPrint and extended connectivity fingerprints, they pick compound B as the closest compound, and that doesn't even have the same number of fused rings. If we look at Saagar features, they give highest similarity of 0.98 between compound A, which has the right number of fused rings. The next closest compound is D at similarity of 0.88, which is high, and it also has the right number of fused rings. Saagar feature provides resolution also. Similarity going from 0.98 to 0.72. 0.72 is the lowest similarity with compound E because it has fewer rings and has an extra substituent. So if one were doing a read-across assessment from the chemistry point of view, Saagar will fetch compound A with high similarity, right number of fused rings, and enough distinction from other compounds because Saagar features can capture succinct structural features. We observed many cases like chrycine, but I want to discuss one more case to highlight extensibility of Saagar features. Here again, we picked another aromatic hydrocarbon active analog, diaminomalonitrile, as a query, found the closest compound with each of the 5 fingerprints. Window S shows the compound fetched by Saagar. Structure P was fetched as the closest compound by PubChem, M by Max, and E by ECFP4, and this structure was fetched as the closest compound by ToxPrint. The similarity of all these fetched molecules with query is shown here, which is very low, which is good because the chemistry of fetched compounds, as you see here, is very different from the chemistry in the query molecule. But it is possible that these fingerprints do not have bits or features to recognize the chemistry present in the query, like 2 cyano groups separated by 2 carbon atoms, or the nitrogen of the cyano group separated by the amino group by 2 carbon atoms, and so on. Saagar set, because it is not fixed bit feature set, one can add to it looking at what is missing in the coverage. One can readily code the missing features as smarts and add to the feature list and repeat the analysis. In this case, for instance, based on the lack of appropriate coverage of query, one could extend Saagar set by adding 2 new features like this. And people can think of adding anything more. So here what I'm showing is a nitrogen attached with 2 hydrogens connected to a carbon which is not part of the ring, connected to a double bond which a carbon not part of the ring. So something like this. So one can think of how to fill the gap of missing coverage, add to the Saagar feature list, and repeat the analysis. This extensibility actually can come very handy when dealing with new proprietary chemistries in drug discovery, for example. So that concludes the first experiment showing the success of Saagar features as compared to commonly used fingerprints in active enrichment efficiency, in quality of fetched analogs, and extensibility. Now we put the Saagar features to test number 2, how good and interpretable QSAR models Saagar features will yield. For the QSAR test, we developed QSAR models with data from TOX21 high-throughput assays, modeled 41 data sets, each at 10 micromolar and 100 micromolar thresholds, used 834 Saagar features as descriptors, and for comparison, developed models with moderate descriptors, which has a list of 1825 descriptors, employed recursive partitioning method, and then compared the performance of Saagar and moderate models. We chose to use recursive partitioning because, recall, our focus was to develop interpretable models. And for such models, not only the descriptors have to be interpretable, but the method also should aid in model interpretation. The recursive partitioning method provides a simple, straightforward decision support tool by labeling each prediction with complete decision path. And further, because the size and the class distribution in each prediction node is known, one knows the power and confidence of each prediction. In a five-fold cross-validation test, the average absolute difference in area under the ROC curve between 80-odd Saagar and moderate models is just 0.02. And in a detailed analysis comparing accuracy, NPV, PPV, and area under the ROC curve for 5 representative sets, Saagar performed better than moderate in 14 of 20 comparisons. Saagar performed as good as moderate in 3 of the 20 comparisons, and Saagar performed a bit inferior to moderate in 3 of the 20 comparisons. So one can conclude that Saagar descriptors yield models better than or as good as the models using moderate descriptors. While that is gratifying and encouraging, the real added advantage of Saagar models is in providing chemistry-based reasoning for each prediction and aid in designing molecules. In the interest of time, I'm going to present one example, but you will get an appreciation of how Saagar recursive partitioning models achieve this. Let's look at the model for vitamin D receptor agonist. This is a relatively simple model, 3 layers, and built with 370 compounds. The core node has 50-50 almost distribution of actives and inactives. There are 189 inactives and 181 actives. So how do we interpret this model? The feature 013, which is number of carbon atoms, splits the core node into children node 2 and 3 with 213 compounds and 157 compounds. Node 3 is a terminal node. That means predictions will be made from this. And what it says is that the compounds which have more than 25 carbon atoms are likely to be VDR agonists. Why? Because there are 157 compounds in this node, a large enough sample, and 90% of those are actually active. But should we accept every prediction? No, that's a word of caution, because one must compare the similarity of the query molecule with the similarity of compounds in this set, and that provides what we call as the applicability domain check for that particular node. In this particular case, however, we tested this model with 2 molecules, allocalcitol, which has 29 carbon atoms, and algocalciferol, which has 28 carbon atoms. They are both actually VDR agonists in the literature, but they were not part of the 370 compounds in the training set. So what else can we deduce from this model? We can look at this path here, molecules which have less than 25 carbon atoms, and 4 or more occurrences of feature 382, which is oxygen connected to the middle carbon of a 3-carbon chain, and 3 or more occurrences of feature 829, which is number of hydrogen bond donors. All those compounds are likely to be active, and this node, which is the terminal node, has 17 such compounds satisfying all these 3 conditions, and they are all active. And here we show a representative of molecule which has all these 3 features. Here we are showing the number of hydrogen bond donors in red and the feature 382 highlighted in blue here. How does this model aid in designing molecules? Let's say we were looking to make molecules which are not agonists of VDR. One will start with its node 4 because it has 189 compounds and 170 of those are actually inactive. Well, how does one get here? One gets here by looking at feature 013. That means molecules which have less than 25 carbon atoms and less than 4 occurrences of feature 382, they are likely to be not agonists of VDR. So this is how Saagar features build models which one can interpret and have chemistry-backed reasoning for every prediction, and it can help in actually designing molecules also. So one can conclude that Saagar features not only lead to good predictive models, but also interpretable models. So hence we can conclude then Saagar set is a parsimonious endpoint agnostic set of substructures for cheminformatics applications. For read-across applications, in an elaborate benchmark study, Saagar set performs better than or as well as MDL max keys, PubChem fingerprints, Tox fingerprints, and extended connectivity fingerprints in extracting actives. Along with recursive partitioning, Saagar yields interpretable predictive models and performs better than or as good as moderate descriptors. Saagar recursive partitioning models can lead to probable hypothesis for mechanism of activity. Saagar set is rationally extensible, as we saw in an example. And coded as smarts, Saagar features can be processed independent of any third-party software. And where do we go from here? We will be providing free access to Saagar version that was discussed today for non-commercial research activities by government and academic institutions. And others can contact us at our website to access any desired version of the Saagar set. We are developing standalone and web-based tools with graphical user interface for generating Saagar descriptors for a given set of structures. And we are developing, like the TOX21 models that we talked about, QSAR models for select physico-chemical properties, ADME measurements, and toxicity endpoints from public and proprietary data. I would be remiss if I did not acknowledge the technical expertise of my colleagues Jason, Austin, Mihir, and Eric in facilitating extensive parallel computations on high-speed computer servers at SIOM. And in the end, I would like to thank you all for your time and attention. Thank you.